Okay, hello everyone, welcome back. So what we're going to do today is continue with our discussions on substitution and elimination reactions. These are reactions of alkyl halides. So we are still in chapter 7, reactions of alkyl halides. Okay, so substitutions and eliminations. Alkyl halides, substitutions and eliminations. Now, what we've done so far is we've seen two reactions of alkyl halides. We've talked about SN2 and E2. So these are two reactions that we've already covered. Now, I just want to quickly recap, some of the salient features of these two reactions. So for an SN2 reaction, key points that you want to keep in mind so that going forward, we'll be able to differentiate between all of these reactions. Okay, so the key points that you want to keep in mind are SN2. It needs a strong nucleophile that is usually required. It is favored in polar aprotic solvents. And third, mechanistically, this is a concerted process. So the mechanism involves a concerted process. It is one step, and it involves a backside attack by the nucleophile. For chiral alkyl halides, okay, when the alkyl halide is chiral at alpha carbon, the reaction proceeds with an inversion of configuration. Okay, so I think these are like some of the salient features of SN2, because when you think about SN2, I think these things should come to mind. Or when you're trying to identify, if you're trying to look at an alkyl halide and a nucleophile, and if you're trying to predict whether it is SN2 or E2 or the new reactions that you're going to learn, these are some things that you want to keep in mind. And these are some things that you're going to identify. Okay, like, is it a strong nucleophile? Is it a polar aprotic solvent? Is there an inversion of configuration? Things like that, if you have the product, okay? Now, for an E2 reaction, this requires a strong base. And what you have to realize is, I think a couple of times, I think I've been trying to basically repeat this. What you have to keep in mind is that a strong nucleophile and a strong base are often the same compound. There are cases where a strong nucleophile may not be a strong base, or a strong base may not be a strong nucleophile. Okay, there are cases like that, but usually there is a good degree of overlap between these two. So for example, like methoxide, or if we complete it, sodium methoxide, okay, this is a strong nucleophile and it is also a strong base. So a nucleophile always has some basic properties. Whether a strong nucleophile is a strong base or not, that depends. And if a strong base is a strong nucleophile, that also depends. Okay, so we'll slowly learn to identify all of those. But what this reaction requires is a strong base. It's usually favored in polar aprotic solvents. This also involves a concerted process mechanistically. So it is one step, and in terms of mechanism, remember that this involves, or this requires, an anti-periplanar arrangement as far as the beta hydrogen and X, the halogen, are concerned, okay? And then in terms of stereochemistry, this reaction, the E2 reaction, is both stereoselective and stereospecific. Actually, another important aspect of both reactions that I actually left out and which I should add is the order of reactivity. So I'm just going to add it to the top here. So remember, with respect to alkyl halides, the order of reactivity for SN2 is methyl greater than primary, greater than secondary, tertiary. These do not react. Almost tertiary alkyl halides do not participate in SN2 reactions. Whereas for E2 reactions, as far as the alkyl halide is concerned, the order of reactivity is reversed. So tertiary is greater than secondary, which is greater than primary. And then we can put methyl as something that is not going to do this because there are no beta hydrogens. In fact, primary is already very slow. In this case, secondary is really very slow. So, well, compared to the methyl, so it is the slowest of all of them because tertiaries don't do this. So alkyl halide, here it is reversed because the reactivity order is based on the stability of the alkene. So some key things to remember about SN2 and E2 reactions. So what we're going to do today is look at some reactions, two reactions, one substitution and one elimination, that are different from both SN2 and E2. And the difference is mainly in terms of mechanism, okay? So what we're going to do first is, in terms of the number that we're doing, this is the third reaction that we're doing, and this is substitution of alkyl halides, and we will come back and fill that name. What is this reaction? Okay, this is a substitution reaction that we're talking about. Now, a very key difference here for this substitution and the elimination reaction that we'll be talking about is that both of them involve weak nucleophile. Or when it comes to elimination, it would involve a weak base. Okay, so weak nucleophile, and I'm going to put this in here, which is also weak base. Okay, a weak nucleophile. Now, not every weak nucleophile is a weak base. There are strong bases which are weak nucleophiles. So this reaction involves weak nucleophiles and weak bases. Okay, and in most cases, this weak nucleophile, or to make it clear, this is for the elimination reaction that we are going to talk in a bit. For substitution, it is a nucleophile. Okay, so for the elimination, we're talking about a base. In most cases, for this kind of substitution or elimination reactions, our weak nucleophile or the weak base is a solvent. Okay, it's the solvent that that acts as a nucleophile or a base. Okay, so that is the key differentiating factor. In SN2, we had a strong nucleophile. For E2, you needed a strong base. This is a reaction of weak nucleophiles and weak bases when it comes to the elimination part of it. Okay, so an example of this reaction. So this is a tertiary alkyl halide. if we take this tertiary alkyl halide, now remember, since it's a tertiary alkyl halide, we do not expect it to do substitution reactions, because tertiary alkyl halides, sorry, let me correct it. We do not expect to engage in SN2 reactions, okay, bimolecular substitution reactions, because tertiary alkyl halides are too crowded, so the backside attack is not feasible. Okay, so this should not do SN2 reactions. Now, and for something like this to do an elimination, what we know is it needs like a strong base. Okay, so if we take this tertiary alkyl halide and we put it in methanol, and I'm just using a solvent, like a very simple solvent. And now in most instances, this solvent that is used is polar protic. Okay, these are the best solvents for doing this kind of reaction, the solvents that really help this reaction. So methanol, it's a polar protic solvent. So if I take this tertiary alkyl halide in methanol and I heat it, okay, now if you look at the combination here, we have an alkyl halide, which by nature, going back to some of the introductory stuff from chapter 7, realize that alkyl halides behave as electrophiles. Okay, these are electrophilic because we have this del positive on that carbon and the del negative on the bromine. So it's an electrophile. It's an electrophile, and this is a weak electrophile because it only has like a del positive on it. Methanol, the solvent that we are using, this can serve as a nucleophile because it has this oxygen with the lone pairs to it. So it could serve as a nucleophile. But again, realize that this is a weak nucleophile because it does not have a negative charge on it. It's not like loaded with electron density. It's not overflowing with electron density. It only has enough electrons that are required by its octet. In fact, all atoms, they only have enough electrons that are required by octet sometimes, but when you have a negative charge, you have like, you're basically loaded with electrons. There's a lot of electron density there. That is not the case here. It has two lone pairs. There is some electron density there. So it is a nucleophile, but it's a weak nucleophile. So tertiary alkyl halide should not undergo SN2 reactions. This is a weak nucleophile, and since it's a weak nucleophile, this is also a weak base. So since there is a weak base, we do not expect E2 reactions to happen as well, because E2 requires strong nucleophiles. But it turns out when we take this tertiary alkyl halide with this polar protic solvent and we heat it, okay, which is key to get an appreciable rate for most substrates. Now, some substrates might do this at room temperature, but again, the rate goes up as you increase the temperature. Okay, so if you heat it, we get two products from this reaction. These two. Now, if you look at your starting material and you look at your product, it looks like this first product is the result of a substitution. Okay, so this is a substitution product because we substituted that bromine, the halogen, with looks like this OCH3, which is part of the solvent, or which was our nucleophile or a base. Okay, and so that is a substitution product. This is a substitution product. And over here, we have what looks like an elimination reaction, elimination product, because we've lost the bromine, the halogen, and we've lost one of the beta hydrogens in some sense. So this is an elimination product. So I guess I just realized that I think what we're doing right now is we are basically discussing both combined. So we should probably go fix this, say elimination, and we can go ahead and fill out what reactions these are later. Okay, so we're discussing both substitutions and eliminations because I did talk about bases there. You know, a lot of things are basically common here. I was initially planning to split it out, but I think it is combined right now, so I think I'll just keep it like that. So these are two products that you get with a tertiary alkyl halide, which is a bad substrate for an SN2 kind of reaction, but we get a substitution product. A weak base, but we get an elimination product from an alkyl halide. So the question is, how does this happen then? Because our substrate's a weak electrophile, our base or nucleophile is a weak nucleophile. So how are we getting this reaction? Okay, because this should not do SN2. So what do we know about these reactions? Okay, what do we know about these reactions? Again, in terms of like mechanism, okay, like when you do studies, what did people find? What they found is the rate of the reaction only depends on concentration of alkyl halide. So there's only one dependence. There is no nucleophile or base that shows up in the rate. So that means the rate law is something like rate equals to a constant times concentration of the alkyl halide and to the power 1. So the overall order of this, so that means if you double the concentration of the alkyl halide, the rate doubles. But if you change the concentration of the methanol, which now realize I already said it's a solvent. Okay, so it's usually a solvent. So this here basically is our solvent. And so if it is a solvent, it's present in excess. There's like a lot of it. So there isn't like a lot that you can change about its concentration. So it is independent. So this rate is independent of the concentration of the solvent. Doesn't matter how dilute or how concentrated you make. The rate only depends on the concentration of the alkyl halide. So based on this, okay, because the rate only depends on the concentration of the alkyl halide, again, going back to some of the previous discussions, what that means is our reaction has a step which only depends on the alkyl halide. The solvent does not show up, or the nucleophile or the base, whatever you define this as, that does not show up in the rate limiting step. Okay, so for that reason, these reactions are called SN1, so substitution, nucleophilic, and unimolecular, and E1, elimination, unimolecular. That means there is only one molecule in the rate determining step in some sense. Okay, that is what we're saying. It depends, the rate dependency is only one of the reactants. And like I said, for simple reactions like this, it always relates to the rate determining step of the reaction. The rate law actually gives us a picture about what is going on in the rate limiting step for simple reactions. For more complex reactions, that is not the case. Okay, so it is SN1 and E1. So the rate depends on that. So, and what that suggests is, since we have an alkyl halide and we have the solvent and everything, what that means is this reaction cannot happen in one step. Because if it is only one step, then how do you get this products? Okay, because there's only alkyl halide in the one step. So it is more than one step. In fact, this is a two-step reaction. So we will see the details of those reactions. So I'm just going to write out at least one of those terms. So essentially this is substitution, nucleophilic, and unimolecular. Okay, and what we're going to do is in subsequent videos, we're actually going to look at the specifics of each of these reactions, like what does SN1 look like, what does E1 look like, okay? And the other thing that I just want to kind of preview right now is that SN1 and E1, okay, since they happen in scenarios like this where you have an alkyl halide with a solvent, they always happen together simultaneously. It is very hard, okay, there are exceptions, but it's very hard to separate these out or to tease them apart. If you try to do an SN1, then you're going to get E1 product at the same time. Or if you're trying to do an E1 reaction, you are going to see SN1 products at the same time. That is how these reactions work. So it is very hard to separate these out, okay, to have only one of them happen and the other one, and not have the other one, okay. Those are exceptions, actually. Those are possible, but those are exceptions, okay. So the subsequent videos will go into the details of these, but this is basically like an intro to SN1 and E1 reactions, okay. Stop right there.